Today, I'm going to explain the purpose of a Latin square and how to construct one. I will also be demonstrating on how a Latin square design could be used to optimize a production process in manufacturing, which is an example of a task that an industrial engineer could be challenged to. A Latin square is essentially a method used to analyze the variation in the two variables under analysis, while conducting an experiment that involves three variables. A Latin square design is considered an incomplete layout because despite there being three variables, we assume that both two and three variable interactions do not occur. It is constructed as a square matrix with one variable labeled at the top of the Latin square and the other labeled on the left side of the Latin square. For each variable, there must be the same number of options under analysis as the results in a square matrix, with the same number of rows and columns. Each variable under analysis of variation should receive each different treatment only once. This means that the Latin square should only have the same type of treatment once in every row and column. It is constructed like this to show how the results of an experiment change as the two variables change for each given treatment. An easier way to understand this is thinking like you are playing Sudoku when each number 1 through 9 can appear in each row and column only once. Once a Latin square is designed like how a completed Sudoku square would look, you have successfully eliminated the external factors that could have affected your results. This is because the Latin square is based off of a random assigning of the combinations of variables and treatments. These are often used in psychology, medicine, agriculture, and engineering to control the influence of random external variables, but today we'll be focusing on specifically engineering. One example of a Latin square within industrial engineering would be comparing the supply yielded from different factories over a given period of time using different methods of production. In this example, we are looking at the number of flight simulators being produced each week at different factories using different production methods. In this example, we have one blocking variable of 5 different factories and another of 5 different production processes. Each of the 5 production processes will be tested once at the 5 facilities over the course of 5 weeks. This will not only yield the results of which production process produces the greatest supply, but it also eliminates the effects that other random variables may have, such as location of the factories and their operational hours. After obtaining results from this experiment, you can calculate a multi-factor ANOVA by calculating the sum of squares, mean sum of squares, and degrees of freedom to understand the variance occurring in each outcome. But that will not be covered in this video. However, you can learn how to do this in one of my classmates' videos. Thank you.